All right, so we've got exponential and logarithmic equations. Exponential equations will not have a logarithm in them at the beginning. Logarithmic equations have a logarithm in them in the beginning. All right, so anytime you see a problem that has is exponential, then logarithms are how you're going to try to solve it. If it's got a logarithm in it, an exponential is how you're going to try to solve it because they're inverses of one another, just like multiplication and division are inverse operations. Logarithms and exponentials are inverses of one another. So let's look at this first one. 2 to the 2x is equal to 2 to the 3x minus 12. That is an exponential equation because each side is an exponential. You've got a base and an exponent, a base and an exponent. That's what an exponential is. Now, because these bases are the same, what should that mean about the exponents? They should be equal to each other, right? Now, the math that makes that possible is that you take the log base 2 of each side. If you take the log base 2 of each side, that's what cancels out those base 2's and makes it where you can set those exponents equal to each other. Set up that equation, 2x equals 3x minus 12. Okay, that's going to be handy when we get to things that are not the same base as we go along here. All right, so got the bases the same, and then we take the log of that same base of each side to cancel them out. And then we get a nice, easy 7th grade math problem to do, right? Yeah. Oops. Maybe it's not 7th grade. Maybe I can't do it. I can't do it. Negative 1x equals negative 12. Divide by negative 1. And x is 12. If you plug that back into the original problem up here, 2 to the 24th power, and then 3 times 12 is 36. 36 minus 12 is 24, so it's 2 to the 24th power equals 2 to the 24th power. So that's got to be equal to each other, right? So we get an answer. We can go back and check it today, which will make some of us feel a little bit more better about our answers because we're not sure. We can be sure that that's the right answer by checking it. Okay, let's look at another one, different. Let's look at 3 to the 4x is equal to 27 to the x minus 1. All right, so this is where our brain power's got to start working a little bit because the bases are not the same. That's the key. 3 will go into 27, but we want to think exponentially with this. So it's not how many times will 3 go into 27, but how can I rewrite 27 as an exponential?
Price and Rebecca Hillis reports the office.
So what do we know about 27? We know it is 3 to what power? 3 to the 3rd. So I'm replacing it with a 3 to the 3rd. So this is really the same thing as 27 and still raised to the x minus 1 power. What's the property for these two exponents right here? You got to multiply them. So that ends up being 3 to the 3x minus 3. All right? This is 3 to the 4x. Now the bases are the same, so I can cancel those out by taking the log base 3 of each side. So taking that log is kind of like taking the square root of each side when we're doing quadratics. It's an operation there. So that cancels out the base 3's. Get 4x is equal to 3x minus 3. Solve that booger. X is equal to negative 3. And if you go back to the original problem, 3 to the negative 12, and then 27 to the negative 4, you could check those with the calculator. 3 raised to the negative 12 is that. And then 27 raised to the negative 4, same number. So that is the correct answer. So we can check there. So nice and easy. So, but we've got to get the bases to the same level on each side. That's the key. Let's look at one that's a little tougher. 81 to the 3 minus x equals 1/3 to the 5x minus 6. All right. So we're dealing with exponential equations here. So we've got to think exponentially. What's the relationship between a 1/3 and an 81?
They're not divided by 3.
They're threes, right? 81 is 3 to what power?
4.
The 4th power. That's right. 3 to the 4th. So I'm going to change that to 3 to the 4th. The 3 minus x. 1/3 is 3 to what power? -1. That's right. Okay. So this is where a strong understanding of exponent rules comes back in, especially when there's fractions in there. So the idea is that that's 3 to the 1st power on the bottom. If you move it to the numerator, it changes signs, and that's how it becomes 3 to the -1 power out of that. If it were 1/9, it'd be 3 to the -2 power. 1/27 would be 3 to the -3rd power. That idea. Okay. Now, what's the rule for the parentheses and the exponents? Multiply them. So that's going to be 3 to the 12 minus 4x and 3 to the -5x plus 6. What gets rid of those 3's? Log base 3's. (12 minus 4x) is -5x plus 6. That's not a bad equation to solve. Add 5x, subtract 12, so the x equals -6. All right. And we could take that back to the original, plug it in, check it if we need to. It works. It's the right answer. Right. So not overly complicated here. It seems to be working out pretty easily. Let's do another one here. Let's do 32 to the x is equal to 1/16 to the 3x minus 2. Again, we're thinking exponentially, not, I guess the right word is multiplicatively, but what's the relationship between 32 and 16 exponentially? Does 4 go into 32? It does, but it's not 4 to a power, right? Because you got 4 squared and 4 to the 3rd. You get past 32 already. So 2 would be the right thing here. 32 is 2 to the what power? 5th. 16 is 2 to the... Yeah, this would be 2 to the -4 because it's 1/16. 16 is 2 to the 4th. So got all the bases the same now. Just work that to 2 to the 5x, 2 to the -12x plus 8. Log base 2 of each side. And 5x is equal to -12x minus 8, or being plus 8, excuse me. Add 12x. 17x equals 8. Fraction answer. That's okay. That happens. So far, everything we've had, we've been able to get the base the same on each side. And then we use the log of that same base and get rid of it. And then we got an easy equation to solve. So if the bases are the same, that's going to be your procedure. That's the way you're going to try to go about that. Well, let's get to one that doesn't quite do that. Four to the x is equal to 11. Why doesn't this one work that way? Yeah, I can rewrite 4 as a 2 as a base, but I can't rewrite 11 as a 2 as a base or as a 4 as a base, right? There's no way, it's not a good number to do that with. But I can still use the same tools that I used to solve those other equations to get rid of the base there of the 4. What will get rid of a base 4? Log base 4. So if I do log base 4 of each side, because whatever I do to one side, I've got to do to the other. On the left-hand side, the log base 4 and the base of 4 cancels out. What's left? X. And then log base 4 of 11 is what's on the other side. What is that? What we did yesterday. It's a number, right? And we can get a decimal approximation for that if we want to. This is the exact solution. The decimal approximation would be just work that out. So I'm going to do math, log base 4 of 11. So I'm going to go 3 decimal places. So 7, 2, 9. That 7 makes the 9 go up. So it'd be 1.730. So using that log base to get rid of the base so we can get that exponent out of it. That's the idea. Another 7 to the 9x is equal to 5 or 15. Is there a relationship between a base of a 7 and a 15 that we could use to do exponential stuff with? No. 7's prime, so it's not going to break down at all. And 15 is not 7 to a power. Right? 7 squared is 49. Definitely doesn't work. But since there's the only thing going on is the 7 to the 9x, the variable's up there. To get rid of that base of a 7, what am I going to do? Log base 7 of each side. Again, it's an operator. It cancels out that base of a 7. And I get 9x is equal to log base 7 of 15. Which log base 7 of 15 is a number, right? But x isn't by itself yet. So we don't want to get the decimal approximation until we get x by itself. So what do I do to get x by itself? Yeah, just divide by 9 like you would any other equation. We get log base 7 of 15, all of that divided by 9. And we're going to get a decimal approximation for that. So I'm going to hit math, log base 7, 15. Get that answer, and then divide that by 9. So going 3 decimal places would be 0.155. Yeah, but you got to plug the exact solution in. You can't plug in the rounded one. The rounded one's not going to work out perfectly. It'll get real close on each side, but it won't be perfect. If you plug this in, and the way that you could do that would be store that as x. So I've got that answer there. I could hit store, which is right beside the 1. Store that as x. And then if I do 7 raised to the 9x, 15, that's the same thing that's on the other side there. That's the best way to check them when it does weird decimal answers like that. Yeah, any equation you're going to be able to check like that perfectly. do one. It's a little tougher. 9 to the x plus 6 equals 41. Okay, we need to get the part that, doesn't have an exponent, get those like terms together first, just like we would with any other equation. So subtracting 6, 41 minus 6 will be 35. Man, I was hoping that'd be like something like 27 or something that we could do exponential, but it isn't. So how could I do that? I could do log base 9. That would work. That'd be x is equal to log base 9 of 35. And we get a decimal approximation for that. Well, yeah, you had to do a step before. We had to do that little extra step there. That wasn't real hard, was it? That's what I hope you all realize. It's not really hard. 35. 1.618. Now, here's what I want to show you. Same problem right beside it. If we jump in at that step, 9 to the x is equal to 35. And I didn't go ahead and do log base 9, but I went ahead and changed that to 3 to the 2x is equal to 35. And I did log base 3 of each side. And then I'd have to divide by 2 at the end. Is that the same answer? Should be, right? Because it's the same equation, same problem that we're solving there. So the decimal approximation for log base 9 of 35 should be the same as the decimal approximation for the log base 3 of 35. So I'm going to check that. So math, log base 3 of 35, bless you. Then divide that by 2. And what do you know? It's exactly the same 2 decimal places there. So what reason I show you that is that you can do it different ways, but exponentially they're equal, right? 9 to the x and 3 to the 2x are the same equivalent expression. They mean the same thing, but we get the same answer when we solve that equation. So if you work yours with a base 3 and use log base 3 to solve it, fine. If you work it with a base 9 and solve it for this problem, that works fine too. So anything like with a base 4, you could work it with a base 2 and it'd work. That idea. So it's kind of hard to mess this up. You can do it different ways and still get the same answer. So you may not do it exactly the same as one of your neighbors, but you check your decimal equivalence. That's the is it right or not? Okay. So and also keep in mind that on a multiple choice test, they may not have this as an answer choice. They may have that as an answer choice. Check the decimal equivalence on those to see if it's the same, if it's on the calculator portion. ACT wise, you got the calculator the whole time, so you can check those, that idea. All right, let's look at number 9. E to the 5x plus 2 minus 5 is equal to 10. Add 5. So get your like terms together. E to the 5x plus 2 is equal to 15. Now what? Natural log, LN, that's right. The base, log base E is the natural log, so we're going to take the natural log of each side. Those cancel out. There's 5x plus 2 is equal to the natural log of 15. And now we got to get x by itself. Remember that natural log of 15 is just a number. We're not going to write out the decimal for it yet. because we couldn't write enough of it to make it work. But so what do we do to solve it for x? Minus 2. So it's going to be 5x is equal to natural log of 15 minus 2. And then last step would be divided all by 5. So natural log of 15 minus 2, all divided by 5. We're going to get a decimal approximation for that. Natural log 15 minus 2 divided by 5. 0.142. Be careful there. Kind of a common mistake would be dividing this 15 by the 5. That's a no-no. It's kind of like when you divide, when we're doing quadratic formula, you couldn't divide into the number that was underneath the square root. Same idea. You can't divide into the number that's inside of the log. Only numbers that are outside. Okay, easy enough. Let's go a little more difficult. And you'll probably say, oh, it wasn't that bad. I hope you do. If you don't, all right, still got to do it. So far, we're still doing all exponential problems here. We're about to swap over to logs in just a second. So, all right, so this one has 5 times 2 to the 3x plus 1 is equal to 30. So, can't do that because order of operations says parentheses exponents happen before multiplication and division does. So I can't multiply the base of a 2 times the 5 because that 2 has exponents on it. So it's locked in there. So dividing by 5, like somebody said, that would be the right step here to get rid of that. So we don't have to worry about doing that. And that's going to be 6. And boy, I wish I'd have been 8 because then I could do exponential stuff, but it's not. So what do I do to solve this? Yeah, if I do log base 2s, 3x plus 1 is equal to log base 2 of 6. And this is a lot like the previous one now. That's 1. And then divide everybody by 3. Log base 2 of 6 minus 1 divided by 3. On the log base 2, you're talking about this because that 6 is locked inside of the log. And you can't do an operation on something that's inside of a log. And what was the number? 0.528. All right. Nice and easy. Okay. Nothing too strenuous about this stuff. It's really not too bad. All right, let's look at some logarithmic equations. Remember, exponentials are going to not have logs written inside of them. Logarithmic equations start with logs inside of them. So log base 5 of 4x minus 7 is equal to log base 5 of x plus 5. Okay, so this one is probably the easiest ones that they come by. If the two sides have the same log on each side, then what does that mean about the stuff inside of the logs? They should be equal to each other. And so the shortcut is you just set those things equal to each other and solve the equation. But what makes the log base 5s go away? It goes back to that property that we talked about at the very beginning. We've got to exponentiate each side, is what it's called. It's an operation that cancels out the log base 5s. The operation is making 5 the base and making each side the exponent. That's what we're doing. And what happens is the base 5 and the log base 5 cancel one another out. That's the operation that's making those logs disappear. Okay. That's going to be handy when we get to ones that don't have a log on each side. If it's a log on each side, the shortcut is how you just set 4x minus 7 equal to x plus 5. Yeah, you can skip that step. But understand that that's what gets rid of it. Because when there's not a log on each side, you can't do that. You can't skip that step. Okay. All right, so this gives us 4x minus 7 is equal to x plus 5. And we want to solve that equation. Subtract x, add 7. So 3x is equal to 12. Divide by 3. X is equal to 4. Now, since these are logarithmic equations, what kind of numbers can we not take the log of? Negative numbers. We can't take logs of negatives. So when we go back to check this, we're looking at inside of the log, is that ended up being a negative number? So if we go back to 4x minus 7, that'd be log base 5 of 16 minus 7, which is a positive number. So that's okay. And then on the other side, log base 5 of 4 plus 5 is a positive number. So that's a valid solution for that. Ends up being log base 5 of 9 on each side, which is correct out of this. So you want to check your answers and make sure that you're not taking the log of a negative number. If you are, that's an extraneous solution. You got to throw it out. Okay, that's what happens there. All right. Let's get one that doesn't have a log on each side. Let's say it's log base 4 of 5x minus 1 is equal to the number 3. So this one doesn't have the same log on each side like the previous example did. And so this is more of a common logarithmic equation that you don't always have the same thing on each side because that's too easy. We couldn't do that to you. So what we want to do is be able to undo this either using exponentiation or rewriting it as an exponential. Remember what we did yesterday when we rewrote problems from logarithmic form into exponential form? How could you do that with this one? What's the base? 4. What logarithms are the same thing as what? Exponents. That's right. So that logarithm is equal to the exponent, which the exponent is 3, and it's equal to 5x minus 1. That's just using the property we used yesterday to rewrite it as an exponential. We didn't do any extra work there, and we get this equation. If we didn't think of doing that, and we just exponentiated each side, so we're going to get the same equation back. So if I exponentiate each side with a base 4, what happens? The base 4 cancels out the log base 4, right? And that gives me the exact same equation as I got before. Either way works. Yeah, what's 4 cubed? 64. Solve that equation like old Algebra 1 stuff. Okay, so either using the rewrite it as an exponential thing that we did yesterday, the same thing as using the exponentiating with a base of a 4. Both ways work. Okay, and they get the same equation to do. So add 1. That's nice. 5x is equal to 65. divide by 5, and it's 13. Go back to the original and make sure you're not taking the log of a negative. 5 times 13 is obviously, and then subtract 1 is definitely a positive number. So, and then 4 to the third power is 64. So that's what's inside of there when you work that out. So it works out. It's perfect. Nice and beautiful math. Yeah. I don't know what number we're on. 13. Log base 7 of 3x minus 2 minus 6 is equal to negative 4. Add 6, because you got like terms there. We're going to get those together. Log base 7 of 3x minus 2 is equal to 2. And now it's either exponentiate or rewrite as an exponential. They are the same thing. I'm just going to exponentiate. And that's just kind of my style of doing it. Whatever way you want to do it. 3x minus 2. 7 squared is 49. Well, now that's an easy problem to do. 3x is equal to 51. Divided by 3, 17. Go back, check it in the log, make sure you're taking the log of a positive number, make sure it works in the problem. It does. Yeah, all right, so you're going to do the 3x minus 2 inside of the log base 7 and work that out, and then subtract 2 from that answer to check to make sure that it equals negative 4. So like you would have to do math. Log base 7 of 3 times 17 minus 2, and then subtract 6 from that. That does equal negative 4, so it's the right answer. So make sure you're doing the log separate from the other math that's happening on that side. Okay. So far, pretty easy, not too difficult. We got 2 logs on the same side and a number on the other side. It doesn't have that log. So this is where the properties that we used yesterday in condensing comes back in. Okay. On the left-hand side, we look at that side because it's got the logs on it. What does addition become? Multiplication. So we could rewrite that and condense that into one logarithm. Because if we can just make one log on that side, it's real easy to get rid of it. We've seen that with the last few problems. So I'm going to rewrite that as log of 2x times x minus 5 is equal to 2. And that I'm going to simplify that a little bit. Write an extra step here. 2x squared minus 10x. So just multiplying that together. So here I'm just showing that obviously we normally just do that one step all together. So condensing with addition, changing to multiplication. And now we need to get rid of that logarithm. What's the base on that logarithm? 10. When it's not written there, it's an understood 10 as the base. So I'm going to exponentiate with 10s. So that'll get rid of the log. Give me 2x squared minus 10x is equal to 10 squared, which is 100. And it's a problem that has an x squared in it and a plain x. So how do I solve a problem like this? That's a quadratic equation, so I've got to do some stuff that I know how to do already. So what do I have to get it equal to? 0. So I'm going to subtract 100 And then what's everything divisible by? 2. So I'm just going to divide everybody by 2 because that's legal and it'll make it easier. X squared minus 5x minus 50, 0. And we got options. We can either factor or quadratic formula on this. I'm going to do factoring. Multiply to be negative 50, add to be negative 5. Negative 10 and positive 5. And I can take the shortcut. Try again. Yeah. And then I set each of those factors equal to 0. We've been down this road before. We know how to do these things. There we go. Now, I got to check both of those in the original problem to make sure I'm not taking the log of a negative. So if I plug in the positive 10 up here in the original, that's going to be log base 10 of 20. And this is going to be log base 10 of 10 minus 5 is positive 5. Both of those are okay. On the next one, if I plug in negative 5, 2 times negative 5 is, oh, it's already out. No matter what the other one does, that one's out. So we're going to, that's an extraneous solution, so we're going to put an X through it like that. So X equals 10 is the only solution that works. The negative 5, is, we found it, but it doesn't work in the original problem because of the domain of the logs. It has to be positive numbers. Okay. Not necessarily. Not always good. It could work. You really do have to plug it back in to check it to make sure. Most of the time, the negative ones are the suspect ones, but they don't always get thrown out. Sometimes they both work. It just depends on the original problem, how it's, you know. Usually, but not always. So you can't, there's no, it really comes back to you have to check them in the original problem. If you don't, then you're not going to know for sure. Let's look at this one. Log base 4 of x plus 12 equals 3 minus log base 4 of x. And this one is a little tricky. So that's a 3 minus log base 4 of x on that side, not 3 times. So we can't move it back up. If it were 3 times the log base 4 of x, then yes, we could make it an x cubed up there. But that's not what we got a minus there. So that's a 3, and then it's subtracting the log base 4 of x. Think about, in general, with most equations that we solve, what do we try to get together first? Things that are like terms, right? So for this problem, in its state right now, what are the like terms? Things that have the log base 4s, right? So how could I move this log base 4 from the right side over to the left side? They're subtracting it, so the opposite, the inverse of that would be adding it. So if I add log base 4 of x to both sides, and then that will be log base 4 of x plus 12 plus log base 4 of x equals 3. All right, then that property says I can condense that down into one log, be log base 4 of x squared plus 12x. Where did I get x squared plus 12x? Multiplied it together. That's what the addition turns into. And then the 4 is the base. So exponentiate with 4s. That's going to be x squared plus 12x is equal to 64. We've seen 4 cubed today. Again, it's quadratic, so that means I got to get it equal to what? 0, and then either factor or quadratic formula. X squared plus 12x minus 64 equals 0. Just for the sake of practicing it, I'm going to do quadratic formula. May be a little rusty on it. I hope not, but it's always good to review. So 144 minus 4 times 1 times 64, or negative 64. Ooh, that'll make a big difference. 4 times 64 is 4 to the 4th power. Is 256 plus 144 is 400. So the discriminant is 400, so that means we're going to have what kind of solutions? 2 real rational ones, because that's a square number too. So that helps us. So when we do our quadratic formula, negative 12 plus or minus radical divided by 2. So it'll be negative 12 plus or minus 20 over 2. So I'm going to work those out. Negative 12 plus 20 over 2. Negative 12 minus 20 over 2. That'd be, 4 and negative 16. Doesn't matter. So those are our 2 possible solutions. We need to check those in the original problem. Pretty easy to check because the original problem has a log base 4 of just plain old x. I don't have to do anything to it. Which one gets thrown out? Negative 16 gets thrown out here. Again, very common that the negative answer gets thrown out, but it's not a requirement that always happens. It's not a requirement that the positive answer always is a solution either. You've got to go back to the original and check those. Don't make assumptions that are not true. Okay. Questions about the last 2? We got one more. One more example. What's up? Yeah, absolutely. Yeah, that's the best way. On the calculator, to store something as x, if you wanted to store 16 or negative 16 as x, type in the number, and then right there beside 1 is this little STO with an arrow. Hit that button, and then hit the X that you would like when you were typing in the equation, and then hit enter, and it remembers, hey, every time you put an X on the regular calculator screen, it's going to use that number until you replace it with something else. All right, last one. Oh, what number are we on? 15? 16. 16 is a good number. It's even. It's a power of 2. It's a power of 4. Square root of 256. I mean, it's wonderful. Log base 3 of x plus 2 minus log base 3 of x equals 2.
Yeah.
Subtraction is division. So if we condense that left side, that becomes log base 3 of what? X plus 2 over x. No, it does not cancel out. You can't. All right. Now we want to get rid of the log base 3, so we exponentiate with 3's. So x plus 2 over x is equal to 9. And maybe if I put this as 9 over 1, it helps you know how to do that problem. How do I?
Mr.
Yeah.
Can Kara tell my step up here?
Yeah, sure. How do I? Go ahead and say. Cross multiply. Exactly. That's, you work it like it's a proportion. You just cross multiply both sides. 9 times x and 1 times x plus 2. That could be 9x is equal to 1 times x is x, 1 times 2 is 2. And then solve that equation. That's an easy one to do. X equals 2, divide by 8. 1/4. And does 1/4 work inside of the original problem? Yeah. All right, so check that in the original. We've got a fraction answer here, so it's a little weird, but it works. You get positive 2 1/4 or 9/4. And then in the first log, and the second log is log base 3 of 1/4, which is legal to have. If you plug that in, stored it, and checked it with your calculator, it works. That's the right answer for that. Okay, so those condensing rules kind of coming into play here, but nothing just too strenuous about what we're doing with logarithms and things. Okay, so